setting up the Technotoy, this, to replicate a DCVG survey, direct current voltage gradient. This in itself is a bit of a misnomer because it should be ground potential gradient, because it is the potential between two places on the ground that we are measuring. I hope that this demonstration on Technotoy will show exactly what I mean. This is the oscilloscope, which at the moment is set on sound. As you can see, it has a built-in sound sensor. This is a data logger with an internal data logging facility, and that is connected to the breadboard, which at the moment has a dry cell battery in place, which is a corrosion cell. Now, you will notice that when I change the dry cell battery that is in place for another dry cell battery, the values will change because, what's that? One of these is bleeping to remind me that it will switch itself off. So, right, to go back to this. This dry cell battery has 1.2 approximately volts of energy, or the potential between this end of the battery and that end of the battery is it's gone down, 1.165. That is because this battery is depleted. Now this rechargeable battery has just been recharged, and I put this in, and the measurement has gone up on this data logger. It's a multimeter and built-in data logger. It will record 40,000 readings, and I will be able to download those onto my computer and plot a graph. Okay, so this is now 31.3204, which is the potential energy between this point and that point. It is measured through the breadboard that I have set up to replicate some of the cathodic protection circuitry that we experience in the field. Coming on to this, which is the data logger through the RS232, which I will now activate, and you will see it appear on the screen, hopefully. So I have to do that through, oh dear. Shrink that down. And this is the, let me find it, 71. 61D. 71. I can't find it. This is the unit. Ah, here we are. Right. This video is being made as I'm fumbling my way through setting this up. Now I'm hoping that this piece of software fires up now. And you will see appearing on this screen in a minute, it's coming through this connection from here, which is a RS232C, which is the it's carried through a light wave. Just one moment. Optical. Here we are. Right, now I'll move this down to the bottom of the screen. This is showing just a fixed reading because I'm not connected. Now I have to push this button for a second, and hopefully that will USB connect. Right, now we have the reading on here, which is on here, but the advantage is not only has it got an analog readout, but it is also recording everything that's going on. So therefore, I now have the voltage between this copper sulfate electrode and this copper sulfate electrode. This one here is at a position between the remote earth, that is this copper plate, and the test post, which is connected to the pipeline, the simulated pipeline underneath the ORAC, which is this part of the demonstration equipment. This copper sulfate electrode is placed on the electrolyte, which is dry, and the electrolyte, the dry electrolyte, is on the copper plate. So this is the equivalent of when you go out in the field and there is very dry, non-conductive material between the two copper sulfate ground contact electrodes. So we have now, this is a replication of, you are somewhere over a coating fault, because this is remote earth and there is a what do they call it? there are resistances, reducing resistances between remote earth and the actual coating fault on the pipeline. And so these have been described as cones of resistance through which the charges must pass to actually register on a monitoring system. Now, this is connected to the Alexander cell, which at the present is not showing any current whatsoever, because this is dry and this hasn't been charged up. So just to complete the circuit, this needs to be cleaned, and that needs never to be cleaned, because this steel will then be anodic to that steel. So, but I won't do this at the present time. All I will do is to wet this so that you can see that charges are passing through the Alexander cell, but that the Alexander cell is not at this present time not primed to be a corrosion cell. It's just part of the circuit. So now I will put some tap water on here. And I will also put some tap water on there. And I will put some more tap water on the electrolyte, which is now you can see that immediately this is fired up, the Alexander cell is reacting as a coating fault on the pipeline, because it is connected to this pipeline that runs underneath the surface here on ORAC, and you will see that there are, whoops, this one needs, this has timed itself out, which is the disadvantage of that. Right, now, you can see that the Alexander cell is reading, this is the amount of corrosion current that is passing between the anode and the cathode of this corrosion cell. This is affected because it is connected to the pipeline underneath, so this is a corrosion cell on the pipeline that we can watch on here as we carry out our surveys and measurements. Okay, now I will get back the, hopefully, bumbling around like an old idiot. I will now get the picoscope back up and hopefully be able to go from sound to scope. And now the picoscope is now recording, this is the oscilloscope, is recording the voltage because it is taken from, the probes of the picoscope are taken from here and from, oops, here. These are the probes from the picoscope, and they're taken from the black and the yellow, which is connected into the circuitry of the breadboard, which is connected to the circuitry of ORAC, which is the simulation system. So now we have a complete recording of the coating fault or corrosion cell, which is at about 1.3 on here, and which is not measured anywhere else. So this is one corrosion cell. This is a corrosion cell here, and if we want to measure the true corrosion potential of this, we can do it by simply moving this half cell. Right, now we have a different reading because I've moved this, I've put it in contact, and let's try and get this in contact. Yeah. So here is a DCVG type reading, and when I move these, you can see that it's being recorded on here, as it's shown on here. So I can now move this half cell. God, this is awkward. I have to do better than this. Whee. And I'm putting this half cell, taking it out of its holder. Whoops. You can watch all the disturbances as they happen and are recorded. Right, now I'm going to put this on the anode of this corrosion cell, and you can see the results And I'm now going to put it on the cathode of this corrosion cell, and you can see the results. So this is moving our DCVG survey over a coating fault from the anode, which you can see on the meter there, see being recorded there, and over the cathode, which is being recorded here, and you can see the negative sign there, and this is all being recorded here. Okay, now I will put this back onto remote earth, and you can see the reading on remote earth. And now I will move this through the excavation. This is now on remote earth. So we have two electrodes, ground contact electrodes, copper sulfate half cells, call them what you like. And they are both in different areas of remote earth. And this is the voltage between them. As I move them towards an excavation, you will see that the voltage changes. We're getting closer to the coating fault on the pipeline. And again, we will get closer still. And we will get closer still. And we will then contact the bare metal in the pipeline with our copper sulfate electrode. So all of this is being recorded, and I will put this back hopefully where it started, from there. Right, now you can see that we've recorded this. Now you should note that the setup at the moment is with a fixed amount of charges coming into the system, and the transformer rectifier is not switched on and the timer is not switched on. So this is the equivalent of a natural pipeline without any cathodic protection or any interference whatsoever. So this is just the very first set of measurements that we can make on this simulation here. So now I will take some photographs of what I've been talking about, so that I can put these photographs up on the presentation itself. The difficulty is that I get reflections on these photographs, so because I haven't got a professional lighting system here. I need a full film crew on this job. I need cameras all over the place, zooming in and all the rest of it. But I haven't got it. Right, that's enough for this little run, and now I'll analyse. I will try now to see if the results that we've got are of any use to us. This is quite interesting because we can actually see the system actually depolarizing here, and let's see what happens when I put this in this position. It's gone up again. So this is the difference between the anode and the cathode on this particular system. To understand these results, we will have to look at the effect of moving the half cell, which is making a measurement between this half cell and that position, a half cell in that position, and you will see that this is positive, and whoops, let's put it in this position, and it has gone, whoops, it's better. Now it's gone less positive. Now let's see what happens if I take the battery out of the system. Now I've taken the dry cell battery out of the system, and that was in fact linked through the breadboard to the pipeline and to the remote earth through the ground bed here. So you can see all the connections. This is the connection from the positive connection from the breadboard system into the ground bed on ORAC. And this corrosion cell, the Alexander cell, is affected by the charges that are actually coming from the pipeline and returning to remote earth here. So now I will change the position from the anode to the cathode here, and the reading has gone up, and I will now put the battery back in. This back to the anode, to the cathode of this system, and I will take the battery out. So in the next series of readings, I will in fact energise the transformer rectifier, and then I will energise the timer.
Okay, let's go.